All right, so in this video, we're going to talk about the selection rules of UV visible spectroscopy. And so the first is called the Laporte rule. This says that transitions between orbitals with the same parity means the symmetry with respect to inversion, are Laporte forbidden. And so what this means is that if you go from a D to D orbital, both of those orbitals are symmetric with respect to inversion. You can think about any of the D orbitals, right? And any of the D orbitals are symmetric with respect to inversion. So let's think about like your typical cloverleaf shape, which is basically the shape of four of your D orbitals, right? They look like this. And so if I were to do an inversion operator on that, well, go from top right down to bottom left, that took dark into dark. And I went from top left into bottom right and vice versa. So I got the same thing. So they're symmetric. And same thing with the old DZ squared orbital. We can shade in the donut, right? And do the same thing. Top went to bottom, bottom went to top, vice versa. So those stay white. Left of the donut was dark. Right of the donut was dark. Those interchange. The donut stays dark, right? So both of these are symmetric with respect to inversion. We call that G, right? Garada. And so because you're going from Garada to Garada, if you're taking exciting electron from a d orbital to another d orbital, that is going to be forbidden, okay? P to P, this will also be forbidden. All p orbitals, doesn't matter the orientation, right? We know what a p orbital looks like. If we do inversion on that, that is going to take dark to white and white to dark. And so those are both, all p orbitals are antisymmetric with respect to inversion. So you went from U to U, and so those are going to be forbidden. But if you go from D to P or P to D, then you went from G to U or U to G, and that is allowed. That's a Laporte allowed. You can also do this same sort of logic, not just with atomic orbitals, but with molecular orbitals. So say you went from a pi bonding molecular orbital that looks like this below, this would be U, right? This would be antisymmetric with respect to inversion because top left is dark, bottom right is white, so those are going to invert, these are going to invert. Okay, this is going to be G, right? Because top left and bottom right are the same, and top right and bottom left are the same. So those would be, that would be an allowed transition, Laporte allowed. We went from U to G, we changed the parity. There's some additional selection rules. These have to do with electronic states. Now, electronic states have a symmetry and a spin multiplicity. So an example would be like triplet A1G. We talked about what multiplicity is. That's the spin times 2 plus 1. That's how we give it a name. So for a triplet, just as for review, that would be spin equals 1. You have 2 1/2 unpaired electrons, 2 spin up electrons, gives you a total spin of 1. 2 unpaired electrons, 2s plus 1 equals 3, we call it a triplet. Transitions between different spin multiplicities are spin forbidden. So going from a quartet A2U to a doublet A2U, that would be forbidden because we went from a quartet to a doublet, the spin change. Going from a quartet A2G to a quartet T1G, that would be allowed because we kept the spin the same. We went from quartet to quartet. All right, and so what does forbidden actually mean? Well, if you're a fully allowed transition, that is going to have a very high extinction coefficient. Now, it turns out that even if you're forbidden on one or both of these selection rules, you still can have a small probability that this transition will still occur, okay? But it's going to be weaker. And so this extinction coefficient, if you remember Beer's law, it says the absorption of a molecule is a product of its extinction coefficient, here I wrote it as epsilon, times C, its concentration, in units of molarity, times the path length of that solution. So usually this is in a cuvette, so usually this is in a 1 centimeter long cuvette. And so the extinction coefficient, absorption is a unitless quantity. Extinction coefficient, therefore, is in units of inverse molarity, inverse centimeter. And so if you have a really, the extinction coefficient is basically the measure of how much per molecule, how much light per molecule something can absorb, okay? And so if you have a high extinction coefficient, like something higher than 1,000 inverse molarity, inverse centimeters, that's typically what we think of as a dye. It's going to be very, very dark. Okay, you only need a very little bit of it to make a whole T-shirt a certain color, right? So it'll be inexpensive in that way. It'll be durable, right? So those are fully allowed transitions. Spin allowed, Laporte allowed. If you're spin allowed and you're Laporte forbidden, those are going to have intermediate values, typically 1 through 1,000. Those are like your typical inorganic solutions, like copper sulfate. You might know if you dissolve, copper 2 salts in water, they look kind of light blue, right? You can see it there, but it's not super strong at normal concentrations, like 10 millimolar. Spin forbidden and Laporte forbidden, if they're both forbidden, these are typically going to be colorless. Now, at really high concentrations or really long path lengths, you'll start to see something, but your eye will have a trouble seeing it at a typical, couple of millimolar concentration. So we need to go over term symbols for molecules, and so these are the electronic states. I trust that in your PChem course you have gone over or are going over term symbols for atoms, right? Think about the ground, electronic states for atoms, how those electrons are paired, and there's rules for assigning those term symbols. For molecules, we're going to go over them now. And so all closed shells, electronic configurations, correspond to the totally symmetric ground singlet states. So these are singlets. They don't have any unpaired electrons. And so, they're going to be singlets with 1, right, denoted by 1. And they're going to be the totally symmetric representation, so 1s across the board. So typically this will be A1G or AG, depends upon the character table, what Molekine symbols used, but it's the one with 1s across the board, the first vector shown. So that's easy. You got a singlet, totally symmetric, singlet. Doublets, 1 unpaired electron, or a single hole. A hole is just the absence of electrons. So that'd be like a D9 state where you have 5 orbitals, enough space for 10 electrons, but you only have 9, that would have 1 hole. So if you have a D9 state or a D1 state, that would be a doublet. Those have the same symmetry as a singly occupied or single hole orbital. So for example, what would the term symbol, how would you write the electronic state, the term symbol for nitrogen dioxide? Well, this has an odd number of electrons. You could write the molecular orbital diagram for this, and you can figure out it's this long thing, okay? All of these are singly degenerate states, right? A's and B's here. They are totally filled. They have 2 electrons. They're singly degenerate. They can only hold spin up and spin down, except till you get to the HOMO, highest occupied molecular orbital. And that's this 4A1 state, and it has 1 electron. So this is a doublet. And so we would call this doublet, and we give it a symmetry A1, because this doublet, this unpaired electron, occurred in a molecular orbital with the symmetry A1. So it's as simple as that. For multiple unpaired electrons, these require more sophisticated methods, and we will just look those values up. So if you have like a triplet state, that gets a little bit more complicated. I can refer you to references that show you the rules to how to come up with these. It's not really important for this course. I'll just give you the values that we need. As you'll see, this chapter will get complicated enough as it is, so I'm just avoiding this topic. But I do want you to know how to write term symbols for singlets and doublets.